Okay, this is exciting. This is the first big concept that you encounter in calculus. It's the concept of a derivative. Okay, we're going to work it out from first principles. The question that the derivative answers is if you have a point on this curve and you want to know at that point how fast is the curve increasing or decreasing, that's what the derivative measures. And it does this by using the concept of slope. The problem is that usually when you calculate slope in an algebraic context, you have 2 points and you connect them with a straight line and you find the slope between those 2 points. All right? So when you have a curved function like this one here, that doesn't quite work. So that's why we have this concept of a tangent line. And that's what I've just added in here. This tangent line approximates the speed of increase of the function. So you see if I zoom in here, when I get really close, you can see that the green curve and the tangent line are going in the same direction, but only at this point here. As you move farther away from that point, the green curve continues to curve away, and the tangent line just continues to go straight. Okay, so that's the concept of a tangent line. The reason why the derivative is an exciting topic is because it represents the rate of change of a function. So it tells you how fast the function is increasing or decreasing. So as an example, if this function represents the position of an object, then the derivative is a way to calculate the speed of the object. It doesn't just work for that example though. If this function, the green function, were to represent the velocity of an object, how fast it's moving, then in that case the derivative would represent the change in velocity, which is called acceleration. If the function represents something else, for example, the number of confirmed cases of a particular disease, then the derivative, again, it's a rate of change. So in that case, it would be measuring the rate of change of spread of the virus. So normally when we calculate slope, like I said, we take 2 points and we calculate the slope between those 2 points. And then that's not possible with a tangent line because it only crosses the function at one point. It only intersects at one point here. So we need to add another point on the curve, and this is where we have to get a little bit creative. And what we do here is we draw what's called a secant line. Secant line is just a line that connects 2 points on a curve. Okay, so you'll notice that the secant line I just made, it is increasing just like this tangent line, however they have different slopes. The concept of the derivative, and this is what we're going to work toward here, is what happens as this point gets closer and closer to the point in question where we want to know the tangent line, right? As you can see, as those points get closer and closer, the secant line gets closer and closer to the tangent line. Okay, so I'm going to take the tangent line away for a little while. And we're going to start to quantify some of this stuff here. So if we know these 2 points and we want to calculate slope, we have to know the x and y coordinates. So we're going to make up some values for those things. For the x coordinate of this point, we can measure down to the x-axis, and we are going to call that point A. So this is just some number A. We're just being very general here. It doesn't really matter what this number is at the moment. Okay. We can also measure the x-coordinate from this point. So measuring down to the x-axis. We're going to call this one x plus h. And what that really means is it's just some number that's bigger than A. If we take this coordinate and we add a certain amount to it called h, then we end up with this other point here. So what we end up with is h is the length between these two x coordinates. Okay, so that if you think about the slope formula, this is the delta x in the slope formula. We can do the same thing with the y coordinates. So if we take this point and we try to find the y coordinate, remember if this green thing here is a function, and we know the x value of this point is a, when we trace this back to the y-axis, the value of that y-coordinate is f of a, right? It's just the output from the function when the input is equal to a. That's just function notation. Same thing for this point here. Let's see, the x-coordinate of this one is a plus h. So when we trace that back to the y-axis, the value of that is f of a plus h. In other words, the output if a plus h is the input into the function. Okay, so if we're calculating slope, we need to know what is the difference between these two y coordinates. In the slope formula, that's delta y. And the difference between them is the top one minus the bottom one. So it's written like this. It looks kind of complicated, but again, it's just the top y coordinate subtracted by the bottom coordinate. Okay, so we have our nice little triangle set up here. This is delta y, and this length here is delta x. And hopefully you remember from algebra early on that the slope is the change in y divided by the change in x. So delta y divided by delta x. And that looks something like, okay, well that's all fine and good, but again, that is for this secant line. What we're interested in is the slope at this particular point. We want to know what is the slope of the tangent line. The secant line is kind of good, but it's not good enough. So what we do is we want to take this point and we want to move it closer and closer and closer to that original point, so we get closer to a tangent line. What's interesting about this, and I'll go back and we can shrink it again, is that watch h here. What's happening to h? H is getting shorter and shorter and shorter and shorter and shorter. If we wanted to make these 2 points exactly on top of each other, h would have to be 0. Right? H gets smaller and smaller and smaller. So here is where we can connect with the concept of limits, because what we really want to do is we want to think about what happens to the slope between these 2 points as h gets smaller and smaller and smaller. And the way we write that is like this. So this, again, just represents the slope between the 2 points, but now we're considering the limit as h approaches 0. As h gets closer and closer to 0, what happens to that slope? And when we ask that question, the answer to that is called the derivative. It's written like this on the left. That is not f to the power of 1, it's called f prime. So this is f prime of a. In other words, it's the slope of the tangent line when x is equal to a. Slope of the tangent line at this point here. The conceptual understanding of what we're doing here is really important. So if that discussion on slope didn't quite click, I really recommend going back, rewatching that step by step and pausing the video just to make sure you understand each step. So there are people who get really excited by these big conceptual ideas, like taking the limit of slope as 2 points get infinitely close together. I'm one of those people. I get super excited about that. However, I understand that there are some of you who might just be interested in knowing how can I apply this to solve problems, so maybe we should do a couple examples as well. How we can apply this formula, which again is called the derivative formula.